All right, we're working on a word problem here, just to finish up section 11.3. And before we look at the word problem, I just want to go over some notation here. Whenever I do geometric series or sequences, it helps me to sort of go over these variables. And sometimes I make a chart like this with n and a sub n. And that helps me keep those two things separate because basically, for these types of problems, the number of terms n, that's x. That's the input. And then the actual series, a sub n, it's y. For example, a problem you might get a series that's just 3, 9, 27, dot, dot, dot. The series A, or the sequence A, is 3, 9, 27. Well, what's not said when the problem is given to you, but what you know is like, well, this is the first term, this is the second term, and this is the third term. It's like the unspoken input. And then the sequence itself is an output. And then you have to figure out a rule to convert this unspoken input into this output. And that's what we're doing a lot of the time with these types of problems. So with that as a backdrop, reading the problem, it says, in 1990, the average monthly bill for cellular telephone service in the United States was $80.90 for the whole year of 1990. The fact that it's monthly, we're not caring about. We're just saying, like, we take all the months, we average them together, and we get $80.90. So from 1990 through 1997, the average monthly bill decreased by about 8.6% per year. So write a rule for the average monthly cellular telephone bill, A sub n, in dollars, in terms of the year. Let n equals 1 represent 1990. That will make a little bit more sense in a minute. What's important about this sentence, in terms of the year, is that this is often the case that a function, f of x, is stated in terms of x. The in terms of is usually the input. So that thing, the year, is the input. So 1990, 1997, those are going to be inputs. The output, average monthly cell bill in dollars. So using that information, I start to fill in my table, my inputs, 1990, 1991, all the way through 97. That's what we're looking at. The output, in 1990, it's 80.9. That's enough information to start plugging into my formula. I have a formula for geometric series and sequences. It is a sub n equals a sub 1 times r to the n minus 1 power. So I know a sub 1 is 80.9, so put that in there. I know r, well, I don't know r. I'm given that, but I figured it out. You can probably see how. It would be easy to say r is 8.6%, but really it says this rate is going to decrease by 8.6%. So 100% minus 8.6% gives me 91.4%, or 0.914. And if I'm decreasing by 8.6%, I'll constantly get 91.4% of my answer every time. So my rule for this function is 80.9 parentheses 0.914 raised to the n minus 1 power. Now, remember this problem said, underlined in green here, n equals 1 represents 1990. So n equals 1 is right here, and that fits, because if I plug in 1 for n, that makes this is 0 power. It means 0.914 to the 0 power is just 1, meaning that 80.9 is my result at this point. So n equals 1 here, n equals 2 here, and n equals 3 here. And I'll put that in parentheses there. equals 3 here, and equals 4 here. And that's important because the next part of the problem says, what's the cell phone bill in 93? So n is 4 in 93, so we plug in 4 to our function. And we get 80.9 times 0.914 to the third power. So we do that we do that on a calculator, 80.9 parentheses 0.914 to the third, did I say to the third power? And I get 61.77, so that is what I want right here. I got 61.77 in 1993, or 61.8, and that's my answer to B, $61.78. 77 cents. When did the average monthly cell bill fall to 50? Well, again, now I'm plugging in the same formula. Here we plugged, to find 61.77, we plugged 3 in for n, or we plugged 4 in for n, and that gave us the third power here, and then we did all the calculation and we got a to the n. Now we want to know, what if a to the n is given as 50? Like, exactly what do we have to raise this to? How many times do we have to raise 80.9 to this power to get 50? In other words, 50 equals 80.9 times 0.914 to the what power? And yeah, we're going to minus 1, so we can look at it that way. We'll divide by 80.9 on both sides. Get 0.618. So 0.618 equals 0.914 to the n minus 1 power. So that means n minus 1 is the log, or excuse me, 0.618 is the number. What are we doing here? If I have 3 to the x equals 27, then I could say log base 3 of 27 equals x. So here I can say log base 0.914 of 0.618 equals n minus 1. I can use change of base formula to evaluate this. This change of base formula, that this is equal to log 0.618 divided by log 0.914. Now I'm worried that I'm getting those. Am I reversing those? Let's double check. Log 6 of, or here we'll say log base log base 100 of 10,000 equals 2, right? Is that equal to, it's equal to log 10,000, which is 4 over log 100, which is 2. So what I've confirmed is that change of base formula, the way it works, to solve this, I put log this number divided by log whatever the base is, this here. So this little number, and the sub goes in the denominator. All right, so I do some calculations now. 0.618 over 0.914, so that's going to look like this. And we get 5.35 as our answer. So 5.35 equals n minus 1. And so n equals 6.35. So at 6.35 is when this thing hits 50. Is when this thing decreases to 50. So it's at 1, 2, N is at 2, N is at 3, N is at 4, N is at 5, still not there. N is at 6, still not there in 1995, but at 6.35 it's going to get there. So close to around here is where this thing happens, where N is 6.35. So sometime probably in 1995, around 1995, that's when this thing is going to get to 50. The end.